Thank you. You're awesome because you got through all the conference. So I'm the last talk here. And so it's just me between now and the after party, I guess. So yeah, bear with me. First, some words about me. I'm Andreas Reischuck, and I do a lot of C++. I also do lectures in C++ and do Qt. So I'm not from the embedded world, but I have customers in the embedded world, and this whole talk is about the story of it. So you find me as ArtMind on the interwebs, so on Twitter, GitHub, and so on. So if you want to contact me, feel free. I have my own company at HicknHack Software. We do C++, Qt, as I'm doing it, and much more. So if you need help with whatever, modern C++, embedded, CMake, please feel free to contact us. So, and also, if you want challenging work, we hire remotely all over Germany, and you can work for us. So with that, let's start the talk. So it's about the story of code, how it evolves. And it's from a customer, but I have to change it to make it slideware, because in reality, everything is a bit more complicated than the story we tell is. But I think I can convey the story quite compelling. So let's start with a ring buffer. I would guess most of you know, but let's recap everything. And first start off, what's the use case for a ring buffer? And the first use case I come up with is an embedded logging system. So you have potentially unlimited data, but only finite memory. What do you do? So you basically have to throw away all the old logs and hope it's not relevant anymore. And then the second use case is like a producer-consumer thing. It happens all over on the embedded devices. So you have hardware constraints, very limited memory, and you want to decouple the producer from the consumer. So we produce many data over time, maybe in quick succession, and then consume it over time from that. A good example is a keyboard. Most of the time, nobody's typing anything, but sometimes they start to type like crazy, and then you buffer that and process it when it's done. And there are many more use cases, so I'm just covering some. And with that, we have the use case. We want to use a ring buffer. What is actually a ring buffer? I try to give a very basic thing. So you can think about it as a circular memory. I have 8 memory cells here, indexed from 0 to 7, like you want to do it. And then you have 2 indices, one for reading and one for writing. And this is the empty state, how we initialize it. So both indices are 0. And once you write to it, then you have one cell written, and the write index is incremented. You can write again, increment the index again. And read, consume it again, and now it's empty. So it's empty because both indices are the same value, point to the same memory cell. And now we write again, and now we have a burst, and the buffer's full. And that's a strange thing because there's one cell missing. But what would happen if we write to that? Then we have the indices both the same. So we cannot distinguish between the full state and the empty state. So usually we try to work around that, but sometimes it's a good idea to just leave it empty. Great. So in reality, our memory is not in a ring. So we have a flat memory somewhere. I was a bit lazy, only 5 memory cells here. Initially, it's uninitialized. And we have, for the implementation, 2 indices. So one for reading, one for writing. Again, this is the empty state. Both indices point to 0. And once we write to that, it gets full. So, okay, everybody on the same page, I hope. Let's start with implementing that. And the use case is, again, a logger. So what we have to write a logger. Now we know, okay, we have limited memory. Let's write a ring buffer for that. Now we know what the ring buffer is. So we have to store the pointer to the memory, know the size of the memory. So we know when to wrap, and also a read index and a write index. And notice we use 16-bit integers here because we know we are embedded. We don't have so much memory. 16-bit is enough for almost everyone. And as it's a logger, it shouldn't be logging more than 64K. Otherwise, the memory is too exhausted. So we initialize it with a pointer to the memory and the size, and then have methods. Like we want to write to the buffer, and we say, okay, we have certain bytes we want to write. Return a bool if some bytes was not written. So the buffer is full, basically. Let me know, okay, maybe you want to block, and then we'll try again later, or whatever. And for reading, we have also a method. We say, okay, here's a memory buffer, read whatever you have, and give us back how many bytes you have read from the ring buffer. Okay, that's the basic methods, and we can also say, okay, let's clear that, reset it to 0. Also, like, inspect it, how many bytes are actually in the ring buffer right now, and also what's the total capacity we can expect. This was the first implementation. It worked for our logger very well. But yeah, the story wouldn't end here. So what happens if the buffer is full? Right now, for the logger, we said, okay, when it's full, then we delete the old data. But we might have different use cases where deleting the old data is not the right thing. So we know when it's full, data is lost. There's no way around it. But we can decide if we reject the latest data or the oldest data. And depending on the use case, either might be viable for your use case. So, good idea. Let's implement that to our ring buffer. So we add a bool that states just overwrite the data. And if we are not overwriting, we reject the data, the latest data. If you're overwriting, the oldest data gets deleted. So we extend our constructor and basically say when the ring buffer is constructed, we know if we do overwrite or not. That's all the changes we need. Internally, of course, we have to change the implementation a bit, but from the outside, that's the perspective. Okay, now everybody should be happy. So now, of course not. Now someone comes around, we need to test. So we need to have a mock implementation of our ring buffer. So we know from components that write to the ring buffer what they're actually writing to it. Because right now we have limited ways to inspect the ring buffer without consuming the data. So it would destroy the data. So to get that, we say, okay, let's write an interface for that. Best practice, not a big problem. Extend our class with the base class, the interface, and all our methods are now interface methods. And we are implementing it in our class. Not a big change for us. Customers happy. Can measure what goes in, what comes out. All good. Yeah. Some time goes around. A new requirement. Basically, we thought with the interface, it's enough. No, we need to preview the data. For example, if you have a measurement in your system, you take a long time series of data, and you don't want to throw away by consuming it, but you want to calculate, for example, the average of the last hour temperature or something like that. So new use case needs a new interface. So, and again, we can decide, do we want to read the oldest data? So basically consume all the available data, might be a viable use case, or start with the newest data, like reading the 10 last measurements. Yeah, let's add that to our ring buffer. And yeah, first thing, let's make it a peek method. So we peek into the buffer, do not consume it, and we give it a memory, like a read method, should work. Okay, we said we have to decide where we want to start reading. So let's add a flag. We want to start from the write index or from the read index. And now it's a bit difficult because we might run a memory constrained environment, so our buffer might not be large enough. We want to consume it in steps. So we also need a peak continue method, where you just pick it up where we last peaked. And we also have to store now the index where we peaked last, and also which direction we have to read. That becomes a bit tricky here, but now it should be everything. No, of course not. Now someone comes around, yeah, it's cool, we can now do measurements, but our measurements also need time points. So we have a little struct where we have a time point and a measurement. And it's very inconvenient because we only store bytes. So we have to serialize our data structure, put it in our buffer, and later read it as a buffer, deserialize it. It's annoying. Maybe we can do something about it and make the interface better for everyone. Let's templatize our ring buffer. So we can store any type that is storable. And also, if you're on templating it, we can also get away and say, okay, let's customize the capacity as a template parameter. No need to store it. Also, maybe the override behavior can be specified as a template argument. Great. So let's do that. So we have our ring buffer definition inherits from the interface so far. And now we make it a template. And also our interface now becomes a template because all the interface now uses T. And also we said, let's do the capacity, the size, and also the override behavior. And now some members can be removed, and we store a standard array. And also the override flag can be removed. The constructor can be removed. Great. It seems like you're good refactoring. You're cleaning up. No, all the methods has to be changed. So now instead of using byte buffers, we use T buffers, basically. And also notice what we lost. We lost our UN16 optimization. And that's the first thing a customer comes up with. It's now bigger. We want back our optimization. Too bad. Now we have to also customize the container type because not everybody is happy with a standard array. So yeah, we basically want to allow optimizations on the user level. Okay, let's add another template argument, default it to standard array, change our buffer storage from standard array to a template container, and also add back a constructor because an array can be constructed in place, but if you have a span or something like a pointer in the range, then we have to initialize that. But now it should be perfect, isn't it? You can customize everything, it's all templated, it's nice, C++. No. Now our customers discover we have standard algorithms. And they want to use that with our ring buffer. So we need iterator support. And just one side, the standard algorithms, and also like a range-based for loop. That would be cool. So we can iterate and consume all our data. So let's add that. First try, we add a begin and an end method. And now we realize, oh, we cannot specify the return types because depending on our container, they might change. And also, yeah, it wouldn't really help much if we extract that from the container. So we would restrict the container or change the interface for that. And yeah, we need a better solution for that. So we dig a bit deeper here and say, okay, we need an iterable interface. So the iterable interface is very basic. It just has an add method, like on the array or the vector. You already have implemented the interface. And we need, of course, the virtual destructor. Never forget that. And then we can build with this generic iterable interface a generic iterator. And this is a bit more cumbersome. We have a lot of iterator traits. And that's basically all deal by I'm using that to present to you. I don't want to show you everything, but I hope you get the idea. So one thing is the iterable is just derived from type T. And we store a pointer to the iterable, so we can call the add method and have a position. And then you add all the other iterator stuff. But I hope you get the idea. So we have a pointer and the position as members here in the generic iterator. And now we add this interface to our ring buffer. Now we know the iterator type, implement the new interface, and now we can specify begin and end. And now we realize, no, we are iterating over the whole container here. But what we actually want is to iterate over the read and the write index. So let's do that. So now we can use standard algorithms, range-based for loops, with our nice ring buffer. But now something comes up. Here we have more standard methods in a vector. Wouldn't it be nice to have all the nice methods of standard vector also in our ring buffer? So let's add that because we can. So we actually go to work and say, okay, like pushback, that might be a good idea. Also like pop front, consume the latest element. Also for that, we need the front, so to be extractive first element. Back might be a good idea. And also, if you are at that, use the square bracket operator. Yeah, but now our ring buffer gets quite a lot of methods. And as you see, there are no longer interface methods here. It becomes really cumbersome to take care of this class. And in reality, we have much more methods, of course. And there are more extensions that might cut out and that came up. For example, you want to use double buffering. So you have a producer over DMA, and that streams all the data in. And then at one point, we want to switch to another one, delay a bit, consume the data, and so on. Then there might be checksums involved. So you want to verify that the content of your ring buffer is correct. And then when we first started with the implementation, there was only one byte that was missing in the full state. But now we store a structure, so we are wasting a lot of memory. So it might be a good idea to have a special full handling so we can fill it up to the full capacity and not lose one entry for that. Yeah, and then we might also, for measurement takes, want to track when it's overflows. So we can later see, there was something wrong, the buffer was full, and we lost like 10 events. So we don't store the data, but we increment the counter for that. And then maybe you can come up with many more extensions for the ring buffer. But yeah, that is not sustainable. Adding features to the same class all over again, and yeah. Oh. There are always more extensions you can add. So what will you do? Do we give up or change our project or to new employee or whatever? No, the only option we have is to make a redesign. But redesign is really dangerous because who will prevent that we fall into the same traps again? So we need a good idea. So the remaining part of the talk will be how to do that. And yeah, so we should start thinking, what is actually here to do? So come up with some questions. And they are very generic, so you can always start with these questions. So what's the special thing here? What is this thing? And then what makes it so complex? What did go wrong? And also then, how could we compose it differently and not fall into the same trap again? And if we can answer those questions, then we might come up with a good design. So let's go deeper on each of these questions. So first, what is special? So the buffer thing is not really special. Buffer is simple, it's just an array. But the ring part, that is a special thing. So then we can ask the question, what makes it ring? And yeah, of course, that's the wrapping of the indices. That makes it a ring buffer. Everything else is just a buffer. Okay, let's remember that and continue with the next question. What makes it go complex? That's not so easy to answer. And it seems like there are so many use cases. Every user seems to be trying to throw another use case into this. So we have to tackle that. And also, there's too many states. Each state in a class makes it more complex. So we have to reduce the states somehow. Okay, let's discuss each of those. So the use cases. What use cases do we actually have? So one use case is obvious. We fill the buffer until it's full. So when it's not full, we write to the buffer. And then it's also, we always write to the buffer. And when it's full, we delete the old data. Then there's a use case like consume the stored data and peek at stored data. And then we have the same variants like from the latest, so in reverse. So the idea that comes up, if we have like 6 use cases, maybe it's a good idea to split those use cases and not write one class that fits all, but for each use case, make one implementation. So how we can achieve that, let's see later. Okay, the other big thing was we had too many states. So let's analyze which state is really necessary and what they are actually doing. So we had the buffer. We actually need the buffer. It's called ring buffer. So without a buffer, it doesn't make sense. So we need the ring or the read index, because that's in the definition of the ring buffer. And we also need the write index. But we don't need the peak index. What is it? And we also don't need the peak direction. It's not essential to the ring buffer. It's an extra feature. Okay, so we feel confident now. Let's start sketching some code and try to make it better. So it's just my idea how to make it better. Your implementation will vary, but maybe I can give you some good suggestions. So first thing, let's start with picking everything in the namespace. So we call it cyclic, because that's the most generic thing I came up with. And now we don't have to prefix everything with ring or something else. And the first thing, let's implement the index, because we said the index that is wrapping is the most relevant thing. So to wrap it, we need to know the size. Let's make that a non-type template argument. And then just what's the index? It's the position. And we initialize it by constructing it with a position. And also, we make a little trick here. We allow non-initialized indices by adding a special uninitialized argument. So it's an empty struct, so nothing is in it. But if we construct this index with uninitialized, we communicate the intention that this thing should not be initialized. And maybe you have a different idea, but that's what I came up with. So, and we then read back the position. And then the main thing here is that we have an add operator. And this wraps. It's the only thing that has a special behavior. And also, we need the comparison operators. So to make a slide short, I just used C++20 default implementation here. But if you don't have C++20, you have to implement the equals and not equals operators to get all the features. But that's all the implementation we need for the wrapping index. And how many customers will want to extend this index class? No, it's complete. You can remove nothing, and that's the goal. If you remove anything from this index class, it won't work. Only extra thing I added is the uninitialized behavior. And that's only to make it more readable when consuming it. And that's the main point of this whole talk here. Next thing, for a ring buffer, we need read and write index. So we need 2 of them. And I thought, yeah, why make a class with 2 members? Doesn't bother me. But in the end, it's better. So it might not be the first sketch anymore, but let's write a buffer index, or buffer indices. So we have the 2, the read and the write index. So we transport the size to both of them, so they both wrap in the same behavior. And we do the same trick with the uninitialized constructor. So we forward the uninitialized values. And then there are 2 methods that are extra here. Now we have 2 indices. We can basically calculate the distance between the read and the write index. And this is the capacity or the size we can consume, or the size that is still available to write. And with this little utility in place, we can come up with the buffer finally. So the buffer, again, just needs to be templatized about the container. So one thing we need from the container, to make it a container, we need to be able to extract the size of it. So it needs to be a constant size container. And store the container, our indices, constructor, uninitialized again. We also need the constructor for the buffer. And then the main meat of this class on the next slide. Okay, so we said we want to separate all the use cases. How do we do that? We still have one buffer class. And the idea I came up with is, let's use a view-like structure for each of the use cases. So we have one use case, write until it's full. And we make that a method and a class. And all this method in the buffer here does is create, construct this instance and return it. There's no behavior involved in this. And that's for all of the use cases. So I don't want to show you all of them. So let's look at the consume use case. Consume, again, is templated over the container. And we store references to both the container and the indices. And both are writable because we want to consume the data. So we have to change the indices. So it's a mutable reference to the indices. And using indices in a class is a bit dangerous because now your class cannot be copied anymore. But I hope this will discourage anyone from storing this in another class. So we just can use now our tools. For example, the size, what we can consume, is just the read distance between the indices. Empty is simple. Iterator is a special implementation. And we have a begin and an end. And begin and end now make much more sense because now we are in the context of consuming it. So we know begin and end should be where it starts and where it ends. And now to show off a bit more, the consume iterator, again, is the same kind of view class, which stores references to the container and the indices. And now we implement the methods. And for example, the indices, incrementing it is just adding 1 to the indices and assigning it back to the read index. So it's very clear, very concise. Hopefully nothing can go wrong here. Reading it is just using the container, this current position of the read index. And yeah, comparing it to the end sentinel is just comparing, is there any read distance left? And that's all. And all the other use cases are implemented just the same. And to summarize it, so we had the idea, We had a universal wrapping index, combined read and write indices, extracted all the details from the container. So we spare us a lot of template arguments, one view class for each use case, and we embrace the iterator and sentinel context here. So we had no interfaces, but would we use interfaces anyways? We can inspect the whole thing. We have ways to inspect that. So I would say don't have a need to have interfaces here. Okay, let's review it. So we split our use cases. We manage the state. So we have very minimal state. We extract all the, it's extendable now without changing the implementation because we embrace simplicity now and it's easy to test. So closing conclusions for the whole thing. Complexity grows over time. And adding all this complexity to one class will not lead to anything good. And minimal design goals. So it's good if you can not remove anything from it. And that's the whole philosophy about it. So, and also think about splitting concerns or use cases, making them their own class. Okay, with that, again, I'm Andreas Reischuck. You find me as Upmind on the internet. You can consult us or work for us. Then there's the C user group I organize in Dresden. Come visit us. I will give you also a tour about Dresden. It's a very nice city. And I will also come back to your user group if you want and give a talk there. So we can start a bit more collaboration. And one more thing, I'm researching languages. So if you want to talk about that, then feel free to contact me. So it's not about like what is modern replacing C++. It's more about what can be expressed in programming languages in general, and especially in system languages, how to make it work. And also like evaluating new languages that come up and yeah, making more sense of it basically. So finally, learn more, learn everything. And that's my talk. Thank you.